Sound check. Testing, testing. Can you hear me?
I can hear you.
Hi.
Awesome.
Let me
Hey, guys.
stop sharing. Okay, so I figured usually we just wait like 5 minutes or so. There was an unusually high number of RSVPs to this event compared to usual, almost 100 people or something. So judging by the square root process you do to figure out how many people actually show up, attendance could be pretty high. So yeah, everyone feel free to talk amongst yourselves and such. I'm gonna go back on mute.
Actually, Ryan, you might want to, well, I can do it. Share the paper image.
Kind of fun to watch people join in real time. Huh. Look at it go. Yeah, while we're waiting, and we're just gonna wait like 5 minutes or so for people to join because of the usual Zoom issues and stuff. Feel free to introduce yourselves, hang out, that type of stuff. Ordinarily, we'd be having pizza and probably hanging out at Uber, but you know, what with the pandemic and all.
Yeah. Well, you'll hear more from me, but I'm Josh. I work at Uber on an effort called data standardization. And that's developing controlled vocabularies and composable mappings for data at Uber.
Hey guys, this is Varaf. Thank you for doing this. I'm actually on the East Coast, but very interesting topic. So thanks for having this on.
Thank you.
Well, thank you, Josh, for presenting.
Maybe you all could do a quick intro to the meetup.
Oh, actually, that's probably a good idea as well. Sorry, people who were ready to introduce themselves. Quick introduction of the meetup. This meetup is for category theory and applications. It is sponsored, if you will, by Connexus AI. That's where I work. Josh is over at Uber. and it's dedicated to exploring applications of category theory, typically in databases, but all over. And it was started as like the Western branch of a meetup that's been going on in Boston for a long time on the same topics. So we probably have some cross-pollination tonight with those other folks. And with that, I'll turn it back to people to introduce themselves. No one else wants to introduce themselves following the meetup description. Up to you guys.
I'll introduce myself. My name is Paul DeFusco. I'm a solutions engineer at Cloudera, and I saw the meetup, and I'm joining for the first time.
Well, it's our pleasure to have you here. Thanks for coming. Other
Nice to
folks
meet you,
want
Paul.
to say hi?
Hey guys, I'm Phil from Philadelphia checking in. First time as well, but I saw the meetup and been doing graph work for a while, so I thought it'd be interesting to check it out. Thanks for letting me join.
Thanks for coming. Other folks?
I'm Tim Havel. I'm here because of Ryan, who I think have a very high opinion of.
Thanks, Tim. How are things on the East Coast? How's the hurricane?
It was a dud in Eastern Mass. I suspect that in the Berkshires it was a bit worse, but really not much here at all.
Good to hear. Stay alive. Other folks want to say hi?
Do my best.
Yeah, I'm Christopher Brown. I'm a PhD student at Stanford, and I've actually presented at this meetup a few months ago, but it's good to be on this side of the...
Yearning for change in this country. Good. The result is a quiet...
Cool. Other people want to say hello?
Paul Howard from Virginia. First time.
Thanks for coming, Paul.
Hi, Pavel from Austin, Texas. First time. It seems that we have a problem at work related to category theory, and I saw at the local meetup this category theory thing and signed up. That's all. Thank you.
We do love category theory around here. Hopefully we can help you with your problem. Other folks want to say hi?
Hey, Chris Pease, data scientist from Portsmouth, New Hampshire. Same thing, background in abstract algebra, and really fascinated to hear about applications for category theory. Thanks for presenting, thanks for organizing.
Cool. Other people want to say hello. I'm inclined to just continue to hang out a little while as people are still coming and going.
This is Katie. I'm a mathematician. Also, I'm in the Middle East of New Hampshire, and sitting here without power, desperately trying to do Zoom on my teeny tiny little cell phone. But I liked the first screen. Algebraic topology is my thing, and professionally, I guess I'm an erstwhile data scientist because I don't like that phrase, but I do a lot of work in property graphs, so I'm curious.
Cool. Well, the presentation is recording, so if you lose power, it'll be available. That's some dedication. Thanks for coming. Other folks want to say hi?
Hey, my name is Divij. I'm the software engineer, and I'm familiar with Josh's work at Uber, so that's what pulled me into this particular meetup. Currently, I'm working with Amazon Lipkin.
Cool.
You sounded like a robot to me, Divij. I don't know about anyone else, but I understood everything. Then again, I know your voice, so I'm not sure if everyone did.
We also may have just lost him on the, oh, there he is. Sorry, people get reordered on the participants list, but yeah, I think that distortion of the audio was Zoom wide. But okay, cool. Other folks? Or maybe it's time to start. We've been hanging about 30 people for a few minutes now.
Yeah, let's get started.
Cool. All right. Well, let me give you the formal introduction. So, hi everyone. Thanks for coming to the meetup. This is Josh. He's over at Uber. Actually, I don't even know like what your title is or anything like that, but you do cool stuff over there related to category theory and property graphs. Thanks for presenting today, and take it away.
Sure. Thanks, Ryan. So yeah, how this is going to work, I will give you an overview of the effort that I'm involved in called data standardization at Uber, as well as a tool that I built called Dragon. So kind of focused on the application of the data model that Ryan will introduce to you in more mathematical depth. So this is a presentation that I gave for the US Semantic Technologies Symposium back in March. So it has a little bit more detail around schema design than we need to focus on here. So certain things I'll be skipping over a little faster than others so we can spend more time on category theory. So just a little bit on motivation. My personal interest in working on data at Uber is to see how far we can push graph technologies and ontology design with respect to making those into fundamental enabling technologies in the enterprise. So there are a lot of companies, including Uber, that have knowledge graphs. Knowledge graphs are kind of trendy, but in general, the data of the organization is not itself a knowledge graph. A knowledge graph is something that exists separately. It may be, you know, a special separate repository of knowledge. Maybe things are ETL'd from other data sources within the company into the knowledge graph where you can then perform queries on them and so on. But there aren't many places the size of Uber where you can find that the data itself is being thought about as a graph, that the data itself conforms to standardized schemas. And that's not the case at Uber either. That's kind of an aspirational goal, which we're starting on the schema side. And my hope is to proceed more to the data side. So the effort I'll tell you more about is focused on standardized schemas and mappings between data models. We'll see what that all means in just a moment. So just a quick introduction to data at Uber. The point of this slide is just to say that it doesn't really matter how much data we have. Yes, we have a lot of data, but that doesn't impact data integration very directly. What's more important to my job is how complex the data is. So how many different sources of schemas do we have? How many different schema languages do we have? What are the barriers to integrating data across these different contexts in which we use the data? And some of them are very different. We have streaming data sources. We have you know, offline data sets. We have microservices that are providing data upon request. So to drill down even further into schemas, if you look at the schemas of the company overall, it's very large vocabulary of around 1 million symbols. There are tons of daily changes to schemas. It tends to be very decentralized, and we have a mix of schema languages. So, for example, Avro for streaming, Thrift and protocol buffers for services, and then a variety of platform-specific languages for storage, and a few internal things. And not a lot of relational data. We do have some. Some good things about our data in terms of data integration. If you're coming from a background of graph databases or semantic web like I do, you might be used to data sets that have kind of a loose schema. You know, certain things are untyped. That's not the case here. So for all of our data, one of the best things about it is that everything has a schema, everything has a clearly defined type. There are issues with those types, which I'll go into, but everything has a type. We tend to have good, strong identifiers for entities. For example, users have a unique ID, trips have a unique ID, and so on. And these things have clear sources of truth to look up those IDs and see what they mean. And that's not a given everywhere. So those are a couple of strong points of our data. Historically, these are some of the things that made data integration difficult and still do to a certain extent. There's a lot of duplication. So you'll find thousands of timestamp data types, hundreds of UUID types, latlons, all the things that we ended up standardizing. You'll find them many, many times across different schema repositories in different languages with no indication that they mean the same thing. So it makes it harder to bring data together after it's been expressed in these schemas that are not aligned. Best practices I won't go into too much. The most important thing to know is that there's kind of been a bottom-up evolution of schemas that are organized by project rather than in terms of any kind of unifying ontology. And that's been done for practical reasons, but it has certain implications for data integration down the road. So data standardization is the effort that we created to address that problem. At the basic level, we simply invent types that can be reused. So I mentioned things like timestamps and UIDs and latlons and so on. Just by providing those types in a standardized way and in a centralized place, we cut down on some of that duplication. So the project has these 4 parts. The standardized schemas themselves, that's the controlled vocabulary. Domain schemas has to do with propagating the standardized types throughout the company, making sure that they're reused, making sure that new schemas are using the types appropriately, adhering to best practices, and so on. What we're focusing on in this talk is data models and mappings. And that's the formal data model. We call it algebraic property graphs. That's actually not a term that's used very often within data standardization itself. That is the formal data model, and then there's an implementation of it called Dragon, as well as some Uber internal tools that I'll talk about. Connected data, that's, it's fun to talk about things you're planning on doing, but that has to do with data discovery and categorization, but that's future work. So we'll skip over this kind of quickly. These are, the standardized schemas themselves. We have things for, basic data types, like URLs and so on. Geoposition data types, units and time and mathematical concepts. Divij, who's on the call, created our infrastructure schemas. We have a data catalog schema that's called Meta. And that's a schema that describes schemas themselves, as well as data sets and data types. Best practices, we can kind of skip over, but that's a set of best practices that can be used regardless of which language you're writing schemas in. And that is basically an informal specification of the data model that we'll talk about in today's session. It has things like primitive data types and sum types and product types. So this is where Dragon comes in. This is a scenario that tends to play out over and over again, not only at Uber, but anywhere you have an ecosystem of multiple schema languages that were not designed together, but need to be brought together. So say you have a schema language X, you need to translate schemas in X to another schema language Y, or vice versa. At some point, so you write a mapping, and at some point you have a need to integrate two that same schema language Y with a third language Z. So you build a second mapping. The problem that you tend to run into is that those two mappings don't compose because there's a different notion of Y in each of the mappings. And there may be, more kind of low-level problems as well, like not being able to integrate the tools themselves. But in terms of a formal mapping, it may just not be the same thing that you're mapping to, because for most of these languages, they haven't been formalized, and the mappings are often not very complete. So what do you have to do? You have to create a third mapping to integrate the one notion of Y with the other integration of Y. And if you do that, you haven't really saved any effort because you might as well have just written a third mapping between X and Z. So you end up with a situation.
Excuse me, Joshua?
Yeah.
I was wondering if you could provide a simple example of that kind of mapping that doesn't quite compose between the two meta languages.
Sure. So for the kind of the languages that we use all the time at Uber, say, Protobuf and Thrift and Avro. So you have a mapping from Thrift to Protobuf. You have another mapping from Protobuf to Avro. And now you want to integrate some schemas that are written in that way. Well, you have a mapping from, you have two ways to map from Thrift to Avro in that case. If you take the one path directly from Thrift to Avro, you get something different than if you take the path from Thrift to Protobuf and then from Protobuf to Avro. So you require some sort of additional mapping, or usually you have to say write some just write some one-off code to integrate those things. Did that make sense?
Yes.
Also, are there other questions? People should absolutely feel free to interject.
Yeah, definitely.
Sounds like no other questions.
Okay,
All
if
right.
not, so this is kind of a fanciful representation of if you have a lot of schema languages, you have all these pairwise mappings. Of course, we don't have this many, but it made it look like the constellation Draco. So the approach that we've
Is
taken.
that actually where the name Dragon came from? Is because this looked like the constellation Draco?
It's the other way around.
Ah, gotcha.
So I presented APG at a seminar last December, the Dagstuhl seminar, and the nickname it earned was Dragon, like a big scary dragon schema. So that's where the name came from.
Gotcha. Cool.
So the approach we've taken is to create an intermediate language that can be used to facilitate mappings between our other physical languages. The disadvantage of this is you have one more schema language to deal with. You had n schema languages before, now you have n+1. The advantage is once you have this language and you have these mappings automatically compose. So if you have a mapping from the Dragon data model to model A here, and you have a mapping to Dragon from model B here, then you can automatically go from B to A, and you have a kind of a formal assurance that if you're, say, taking another path, those paths will give you a consistent result. So the mappings compose. So now I'll tell you a little bit about the data model itself. Early on, we thought about what sort of data model would be needed to mediate between things like Protobuf and Thrift and Avro. And with my background in the semantic web, I was thinking that this would be something like schema.org, which has been one of the most successful kind of top-down upper-level ontologies that's used across across companies, across data sources on the web. So I kind of had that in mind, but when we really got into it, schema.org's model, which is based on RDF schema essentially, was not a good fit. None of the languages that we use support inheritance, for example. So if you really look at the languages themselves, you'll find that they have some common characteristics. So again, these languages have not been formalized. If you go read the thrift spec, you're not going to find anything about product types, but you will find structs. And if you go look at protocol buffers, you'll find message types. If you go look at Avro, you're going to find record types. That's what they're called in Avro. And so you can formalize these things. Go ahead.
Does someone have a question?
Okay, so you can formalize these things in terms of algebraic data types. At least that's the approach that we took. So each of these has some notion of product type. Each of these schema languages has something like a sum type. In the case of Avro, it's slightly different. It should probably have a little asterisk next to it. And then you have various other features that are kind of syntactic sugar on top of product types and sum types and primitive types. Enumerations are a simple kind of sum type in which the type of each field is the unit type. Optionals are basically a sum of the unit type with some other type. So like a 1 plus a kind of type. Type defs are only supported in thrift, but they're fairly important if you want to integrate, if you want to include a graph data model, which we did, and so on. So here's an example of a product type and a sum type expressed in one of these languages. This is thrift, and on the left you have a product type or a struct, which is a type. Any instance of which we have an echo. Yeah, any instance of which has each of these fields. So, and this is not an actual type. Our trip data is a little bit more, has more stuff in it. But essentially every trip has a rider, it has a driver, it has a unique ID, it has a pickup location, and it has a drop-off location, and so on. So anytime you have a trip, you need this and this and this and this and this, which makes it a product. On the right here is an example of a sum type. And again, an enum is a very simple kind of sum type. Whenever you have an instance of place type, it's either food or it's drink or it's shopping. You could think of other kinds of sum types like a shape. If you have a shape, it's either a circle or it's a triangle or it's a square. So algebraic property graphs is the formal data model that we came up with. Again, the goal was to take something, come up with something that unified the physical schema languages at Uber, but was also a graph data model. So I'll talk about how it meets those criteria. Again, I keep saying the same things. It has primitive types, product types, sum types, and then labels as aliases for other types. So in graph terms, for example, I heard property graphs mentioned during the intros. If you have, say, an edge, and that edge is drove for, so a person, a driver drove for a trip. That is a product type, and inside the product type, you have, it's essentially an ordered pair. You need the driver, and you need the trip. So the label of that element then is drove for. And I'll show you a diagram in a moment that kind of connects the labels to the data types. So category theory, I thought, would be a good fit because category theory brings together, it's straightforward to bring together graph theory and algebraic data types using category theory. Ryan will go into kind of the details of what algebraic types look like in category theory. There's a nice kind of intuitive connection between graphs that we deal with in graph databases and categories. And of course, it was important to build mappings that compose. So that was my original motivation for exploring category theory. And then I connected with Ryan, who's an actual expert, to really make this into a bona fide categorical data model. So I'll save most of the technical, the mathematical details for Ryan. But this figure is pretty important, and it's a nice visual. So up here on the left, you have elements. That's basically everything that exists within a graph of data and has identity. So for example, that driver or that trip, or even that drove for edge, they're all elements. Every element has a label, and that's the name of its data type, or one of the names of its data type. So in this case, if you have that drove for, this function lambda maps from the drove for element to the label drove for. And that label is associated with the data type. And that data type, again, in this case, is a product type that gives you that ordered pair. So the type, the sigma or the schema of the drove for label is that specific product type. On the other side, you have the data of the graph, and that's essentially what is contained inside these elements. So you have a drove for. It is an ordered pair. That's here in the values of the graph is where you find that ordered pair. And then that has a data type. So the data type of that ordered pair is that product type. And then crucially, the label of the schema of an element has to always agree with the type, the data type of the value of that element. And that identity needs to be preserved as you map schemas and data. We primarily map schemas between different languages.
Can I interject something here?
You definitely can.
Josh?
Sure. Yep.
So what you're seeing here is a functor G, or what you were seeing is a functor G from a category with 4 objects, E, V, L, and T, and 4 generating morphisms, V, lambda, sigma, and tau. Just a little commutative square category. So associated with each of these is a set, right? A set of elements is what G of E denotes. A set of values is what G of V denotes. A set of types is G of T. So these are all set valued functors. The G is a set valued functor here from the commutative square category. And then this next slide shows a natural transformation of 2 such functors, G1 and G2. So that's where this actually came from. That's where the cube arose.
Yeah, and we don't have to take this completely in order. If there are questions about the mathematical model, we can just jump into that right now.
Oh, I think you should absolutely continue. It's probably better to see the things in context like this than just break out the paper and try to go for it. But I'm happy to pipe up and add some more flavor as you go.
Sure, okay. And so I assume you'll see these diagrams again in Ryan's portion of the talk. But just from an intuitive requirements point of view, what this gives us is the assurance that we can map schemas, data, and eventually queries together in concert in such a way that the mapping is consistent. So if you're mapping a schema together with data that conforms to that schema at the same time, you'll get data that conform, a second set of data that conforms to the map data conforms to the map schemes.
So yeah, I get, there's this question of, so we defined a notion of algebraic property graph, and then we defined a notion of morphism of algebraic property graph. But then there's this other question of, well, what is a morphism of algebraic property graphs actually useful for? Which is a whole other Pandora's box. Yeah, that we'll get to later. Interjection over.
Sure. So this is a little bit, maybe a little bit less formal, but important in practice. So what exactly is a good mapping? Now you can say you have a mapping between two data models. Is it a good mapping? So the way I think about this is it's a good mapping if it's relatively injective, if you're not collapsing too many things. Are often, well, pretty much always mismatches in terms of features that are supported in two languages you'd like to bring together. So what do you do about that? You can kind of think of a good mapping as something that's not only reversible, but does not involve too much collapsing of features. And I'll have a visual on the next slide. So say we have a schema language on the left and a schema language on the right, and there are some corresponding features. A corresponds to A prime on the right, C corresponds to C prime on the right, and then there's some things that don't have any correspondent in the other language, like the language on the left has a feature D that just really doesn't have any equivalent in the data model on the right. So what we do in practice is we stash the features in annotations or in comments. So if there's that feature D that doesn't exist on the right, and this often happens mapping logical schemas to less expressive schema languages like protobuf, Avro. Thrift is pretty good. But we will capture the logical type or other logical features in a comment. And it's kind of a way of cheating and getting back the original feature when you map back. Here's an example. So say we have a logical type here. It's called session events. It's a record type, which is a product type. Has a couple of fields. One of the fields has a data type. It's a list of lists of events. Well, if you're mapping this to protobuf, protobuf does not support lists of lists. There's no way to express that directly. So a couple of things you need to do in practice. You need to transform this data type, which has no direct representation in the target language, into something that does have a direct representation in the target language, and also essentially captures the semantics of the original type. So in this case, we've taken the value of the sessions field and we've promoted it to this internal type sessions value, so this is repeated. So it's a list of session values, and inside the session value, you have a repeated field. If you're going in the other direction, though, in this example, you could actually take this. We have a mapping that takes a type of this form and will give you this back. But in some cases, you might not want to get exactly this back. There's an internal type. Maybe you want an internal type over here. That doesn't have a representation in the YAML syntax, but it is supported by Dragon. This cheater right here, this cheating comment, tells you exactly what the logical type should be that you map back to. So essentially, you're just taking the fully expressed logical type and you're hiding it in a comment. And then when you map back, you retrieve it from the comment and you get rid of this, this helper type. So that's something that we do all the time to capture the logical types in less expressive languages. And of course, if you have two languages that don't line up at all, that don't have any common features or few common features, then it doesn't really make sense to define a mapping. For example, in the degenerate case, if there are no shared features, you could just serialize the entire schema into a string and make that in a comment in the target schema, and then you could map it back and get back the exactly the same schema. But of course, that would not be very useful. So Dragon is a tool written in Haskell that is an implementation of the algebraic property graphs data model plus some additional syntactic sugar. So it is written as in Haskell. That's been a good technical choice. It's also been a source of some organizational challenges because we don't otherwise have a lot of support for Haskell at Uber. So if you never see this tool out in the wild as something you can use, that's probably the reason it didn't happen. I am trying to release the software as an open source project. It's on GitHub, and hopefully it will become open source soon, but there's no guarantee. So yeah, the name came from the Dagstuhl seminar, and the idea of this of a Dragon data model was just, you know, how do we take various graph data models, property graphs, OWL, Shackle, as you can think of it as a data model, and integrate them together. How do we take a query that was designed as a Sparkle query and run that query over a property graph database, or vice versa? There have been a lot of good sort of one-off solutions for those things, but it's hard to then bring together multiple languages in the same framework.
Joshua, I have a question
Yeah.
on that slide. Why Haskell? Why not like Scala? Was there a compelling reason for Haskell?
So the compelling reason is that I felt that Haskell was a really good fit in terms of having deep support for algebraic data types and for type inference and functional pattern matching over algebraic data types. Scala has those things as well, but you know, it's a multi-paradigm language, so it has a lot of other stuff. It would definitely have been a good choice from an organizational point of view to implement Dragon in Scala. Anything that's you know, you can use to create a jar is much more portable. Again, Haskell has been quite a challenge in terms of finding other developers within the company who can help to maintain it. There's a fair amount of enthusiasm about it. There's some, you know, Haskell aficionados in the company who like the fact that it's written in Haskell, but that has been definitely a stumbling block. So if you're thinking of writing a tool in Haskell at a company the size of Uber, you should definitely consider how much of an uphill battle it's going to be to gain acceptance for that choice of language.
Josh, you're breaking everyone's heart with that comment. Oh, man. Sorry to interrupt.
Joshua, did you have anyone that suggested using some derivative of OWL, or that I think it was called prototype system that they used to use to merge RDF with?
So my initial thought was actually to use RDFS, or RDF schema.
Mm-hmm.
So which could be with perhaps some limited OWL support as well. Like I say, I got a lot of resistance to that idea, and I realized that the resistance was actually valid.
Mm-hmm.
So RDFS really wasn't a good fit for the languages that we wanted to bring together. Like I say, there's no notion of subclass inheritance, you know, certainly not property inheritance. It's surprising because there's a lot of development done in object-oriented languages, but when you come to data exchange, it's done in these languages like, again, Avro, Protobuf, Thrift, that are very algebraic and not very OO.
Thanks.
Yeah, so that's what skewed things in favor of a different style of language rather than be using RDFS or L. You know, all that being said, before the COVID epidemic, things looked a lot more optimistic with respect to releasing a Haskell-based tool. We've just kind of, you know, company priorities have shifted in the meantime. Before that, even, there was an effort to standardize on the programming languages that are officially supported within Uber. And of course, Haskell was not chosen as one of those officially supported languages. So it very well may happen when Uber's business picks up again. And I certainly hope it happens, and I'm working towards that. But I can't make the kind of the promise that I made last spring when I gave this talk for the first time, that it was going to happen soon. So here are the basic type constructors. We have name types, which are what we call labels in APG. And essentially that's just a type def, again, like that, that drove for, that user, or that trip type. That's an alias for another data type. Primitive types are, you know, the algebraic data, property graphs data model doesn't specify a specific set of primitive types, but of course, when you go to implement something, you need to support some set of types. So these are the ones that we support. Product types are called record in the YAML syntax. Sum types are called union. Enumeration types, again, are just simple sum types. And then we have some syntactic sugar for optionals, lists, sets, maps. Graph element types, vertices, edges, and properties. There is a notion of uniqueness. So this supports our uniquely identifying fields, like you know, the user's ID, the vehicle's ID, the trip's ID. We have hundreds of these types sort of implicit in our schemas at Uber, and a smaller number that have been formalized. So for example, 2 vehicles can't have the same UID, 2 trips can't have the same UID. If you have an instance of this type, you know, trip ID, you know it identifies exactly one trip. So this is just a quick look at the syntax. There's lots of stuff here that's outside of the data type. So the data type is down here, it's a record type, it has some fields, and then types can be annotated with various metadata, you know, things like links, documentation, example values, sometimes other constraints on the data type that aren't part of the algebraic definition of the data type. An example of a primitive, this is just an alias for string. And this is just extra stuff that's attached to it. So this time zone type is just an alias for string. So instead of using string, you ought to be using this type when you're specifying a time zone. And then our tools can recognize that it's a time zone and not just any string. Record types, again, there's an interval type. Record is something that has fields. And that's, again, a kind of extension to algebraic property graphs. Fields are not named in the abstract data model. In Dragon, they are. So you always have a string index into a product type or a sum type that gives a name for each element. And that's done just because every other language that we're integrating also names their fields. Example of a sum type. If you have a resource manager, it's either it either identifies a Yarn application or a Peloton application. It's one of Divige's types. Enumerations, again, simple sum types. If you have a temporal unit, it's either year, month, week, day. Entities are things with unique IDs. So you see this unique attribute here. that designates a field as something that's uniquely identifying. It's kind of like a primary key. So if you find a data set ID, it identifies at most one data set. So to the question about RDF support, it's not an RDF-based data model, but we do have mappings to a couple of RDF-based data models. We have a mapping to OWL, and we have a mapping to the shapes constraint language, or Shackle. This mapping was created first, and it's been useful for integrating with tools that support OWL, essentially. There's a tool that I use called Grapho for visualizing schemas. If I want to take a schema and see the types and how they're connected, I'll map it to OWL and import it into Grapho. It's especially useful for large schemas that are completely new to us. You can take a schema of a few hundred, a vocabulary of a few hundred schemas, map it into OWL, import it into Grapho, and it gives you immediately a kind of 10,000-foot view of the topology of the schema, which is can be useful in many cases. Shackle is a little bit more of a faithful mapping. So kind of going back to that, that slide on the goodness of a mapping, how well the features align. They really don't align very well between Dragon and OWL, but they align well enough to be useful. The Dragon to Shackle mapping is, you can essentially think of Dragon as a proper subset of Shackle. Everything you can express in a Dragon schema can be expressed in Shackle, up to things that are kind of outside of the data model, like what file do the definitions reside in. So here's
Hey, Josh, we had a question from the group chat, which
sure.
was, what is the main key difference between category theory and graph theory, and why is category theory the better one for database schema mappings?
Well, this is really a question for you. I'm going to let you follow me on this, but graph theory doesn't really have an answer to how to express algebraic data types, how to map between systems of algebraic data types. So it does have answers to things like how do you, things that relate to the properties of a graph topology, graph traversal, and so on. So they're just things that aren't covered in graph theory that are needed.
That's a good answer. So I would have answered, or I will answer it similarly, which is that graphs are great, but they're not quite enough structure for knowledge representation, right? They're these decidable things. They look like context-free grammars, sort of. They're, you don't get enough semantics in them to really do meaningful work. And so we find that data integrity constraints, for example, correspond exactly to that extra stuff that you get out of a category that you don't get with a graph. And so for that reason, right, the data integrity constraints are that like little extra bit between graph and category. That's why we zeroed in on them. And I'm happy to elaborate later as well. And if, yeah, just feel free to speak up for a follow-up if that's not enough of an answer.
Sounds like a great answer to me. So the OSS release, again, this is something I've worked incredibly hard on, and I hope it happens. If I sound a little pessimistic, it's because I got some news today that was not encouraging, but I'm still hoping this is going to happen in an August-September timeframe. There is an article already written for the Uber engineering blog that will be published along with the release, provided the release happens. So the features of Dragon are, again, support for the core data types of APG, as well as additional stuff, list map sets, graph elements, and so on. An API for data model transformations, and that's really what it's primarily used for right now. Kind of nuts and bolts. You have a bunch of thrift schemas. You want to map them into protobuf. You want to create a schema that maps to Avro, but Avro doesn't support includes between schemas, so it's very cumbersome to write more complex schemas in Avro. So Dragon is used to overcome a lot of those difficulties and sort of shortcomings of these schema languages that were not designed with ontologies in mind, that were sometimes not designed with other data integration concerns in mind. So some of the mappings are bidirectional, others are not. So we have readers for the YAML-based format, for thrift, for protobuf with some exceptions. And then we can write to a larger variety of languages. So you can write back to the YAML, you can write to thrift, you can write to protobuf, Avro, Haskell data types, Scala data types, and then the two RDF based mappings. So you can go from any of these to any of these, YAML to OWL, thrift to YAML, thrift to protobuf, protobuf to thrift. And then there's something called, go
Can I
ahead.
ask you a question about the those mappings? You had to build those mappings through a combination, I'm imagining, and please or correct me, but what was your process in building those mappings? Was it getting familiar with the language first and then building out a huge table of which, what were the particular mappings between them? And how do you store it? How are you representing that in Dragon?
Yeah, so the representation is Haskell source code. And I can, maybe I'll let Ryan go first, and then if we have time and we want to go back and take a look at the code, I can do that. I can even give you a demo. But basically, we tried to do as much as possible using these general purpose steps that can be linked together. And there's kind of a last mile step into the specific syntax of the target language. So for example, Avro and protobuf both require certain manipulations of data types in order to get them from the logical data model into either protobuf or Avro. I gave an example of one of those for protobuf, where you can't have a list of lists type. So there's a reusable step that I call type promotion that's used to characterize each of these languages in terms of the features that they support. For example, the top level data types in a protobuf file have to be either message types or enumeration types. None of these other things are supported. You can't define a list type. Avro has its own constraints. Thrift has its own constraints. It's a little bit more constrained, less constrained than protobuf or Avro. But then there are also combinations of the varieties of data type that you, which I call kinds in Dragon. It's kind of a misuse of the term, but like you can, in protobuf again, you can have a sum type, you can have a list type, but you cannot have a sum of list types. So that combination is not supported. There are different named combination of these type kinds that are either supported or not supported for each language. And based on those supported features, the general purpose step will do different things to data types to make them legal in the target language, such as taking a field, extracting its data type, and promoting it to an internal type or even a type outside of the type in which it's being defined. And then again, you need ways of reversing that process in the other direction. So the form that these mappings take are, first of all, a list of reusable steps that are chained together that are specific to each language, or that at least take parameters for each language, telling the transformation what to do for the specific target language. And then there's a final step that takes the transform schema and maps it into protobuf specific data structures. We use the Proto3 API for protobuf. We use language.thrift for thrift. So in the end, you need to map into those specific data structures so you can then say serialize the schema or deserialize the schema.
Yeah, thank you. Yeah, I mean, it sounds like a great process in which you probably teach something from each of those languages that contributed to like the design of Dragon.
Could you repeat the question? You might have broken.
Oh, I was wondering like how a Dragon was informed by each of those. Like, did it change along the way as you like created the mappings for each of the one? Did you? It sounded like, I mean, it sounds like a great learning process for like building out your understanding of what those languages are capable of, and then creating a structure for tracking that.
Yeah, it was a learning process, and it took me in a direction that I wasn't expecting. So I'd never really dealt with algebraic data types. I'd certainly never thought of characterizing, say, property graph schemas in terms of algebraic data types. But in my opinion, it works really well, not only for these data interchange languages at Uber, but also for graphs. So I'm really promoting APG as a graph language as well, and it's informing the GQL standard to a certain extent, or at least I'm involved in a group that's trying to come up with a central data model for GQL. GQL being the graph query language standard, which is to become an ISO standard for graph database schemas and queries. But it started with this, something like this, just a big table, and trying to align the different features that we wanted to support, and then coming up with whatever seemed to be the best fit in terms of a formal framework. And what jumped out to me was algebraic data types.
Joshua, is there a writer for Java or Python?
No, but if this tool gets out there, you're more than welcome to write one. It is something that's actually been requested, not Java specifically, but Go. Whether we can take a set of schemas written in YAML or even protobuf or thrift, and map them into POJOs in Go. Of course, there are already code generation libraries that go from thrift to Go, that go from protobuf to Go, that go from Avro to Go. The problem is when you try to bring these things together. So often I'm asked, okay, I can generate an Avro schema, and then I can generate a protobuf schema, which are logically equivalent, but then you pass them into these code gen libraries and you get POJOs which are not equivalent. So you're sending data over the wire using an Avro schema, for example, and you'd like to then pick it up as using a protobuf based tool. You inevitably have to write some code by hand to map between those POJOs, even though the schema is logically the same. So the point is, if you're able to generate the POJOs directly in say Go, you'd have exactly the same POJOs on both ends, and you'd have a guarantee that the Avro and the protobuf agree with the POJOs.
Thanks.
So yeah, there's also a feature called Polyglot Mode, which lets you read from a combination of schemas. schema languages. For example, there are a few teams that are using the YAML-based syntax to define their own logical types, but they want to depend on the standardized types. So they want to import the standardized schemas and reuse the types. The YAML is not available in all of these schema repositories, but the thrift and the protobuf are. So you can import the thrift or the protobuf as if they were YAML. So Dragon will pick up whatever format it finds and map it into the same logical language, and then you can output it to any language you like. So that's useful for mixing and matching schema languages. So something we're Ryan and I have talked about and formalized in the paper, but I have not implemented in the code yet, deals with schema transformations. So say you have a legacy schema for trips, and now you've written a new and improved schema for trips. How do you map data, or how do you translate queries that were written for one schema to operate over the other schema? So there's a simple language that's part of APG that could, in principle, be used. That's not implemented in code yet.
And good news for people who have to do that, but for SQL data instead of graph data is our product that does exactly that. Should be released sometime this month. So yeah, gotta insert the advertisement there.
Yeah, well, that actually might be a good segue to your segment, Ryan, unless there are other questions on Dragon and applications.
Questions for Josh?
Could you go back to the slide about Dragon, like introduction, like main one, first one?
Let's see, this
one. Okay, thank you. Just keep it, and can I make a screenshot of it?
Yeah, of course. This
the slides
are,
there's a link. Yeah, there'll be a recording posted on the Meetup group. Also, these slides are freely available on Uber's website. There's a link in the group chat to them.
Yes.
Okay, I'm got it. Thank you.
Other questions for Josh?
In that case, I'll hand it over to you, Ryan.
Okay, cool. So yeah, my plan was literally just to work through the paper until people make me stop. So with that in mind, can everyone see my screen? I'll take the silence as a yes.
I see.
Okay. Right, so this paper is the mathematics behind what Josh spoke about, and we should be careful to distinguish Dragon, which is something that Uber's building internally and hopes to open source, from this paper, which defines algebraic property graphs, from the implementation of this paper in the CQL tool that I'll show as well. And that implementation is more about the schema mapping component and such, and less about the components that Uber has already created and hopefully will open source. So with that in mind, we'll just skim through the paper here. So much of this is covered in Josh's slides, but what I want to start with is the actual definition of what an algebraic property graph is, and that's here. So I'll get into this, but before I start, are there any questions for me about anything, really? I don't think so.
I have a question.
Someone in the chat. Oh, pre-scroll left a bit, cutting off beginning of line. Oh no, that's peculiar. Let me zoom out. How's that?
Can we ask questions now?
Yes, please do.
Let's say I have very little idea about this category theory. I just like sort of heard it in several places, and it looks like we should use it for our project, for one of our projects here. So I just want to understand, so you use this algebraic graph terminology, and at the same time there is this categories, definition of categories. I really believe that I read about categories on Wikipedia just now, and I have a question. So what's the difference, and why you use this algebraic graph terminology?
I see. Okay, so that question may require a longer answer than we can really get into here, but the basic value proposition of using an algebraic approach to what we're attempting to do here versus others is the properties that we get out of the schemas and databases when you formalize them this way. So for example, algebraic property graph schemas can be multiplied, added, exponentiated. It's easy to reason about properties they have. And so as I'll show in this paper, and this isn't something that Josh was really able to talk about in his slides, is that there's a rich calculus of operations that you can do on your data when formalized in this data model, in addition to things like move them around that's happening at Uber. So, you know, this is a data model. There are other data models. It will be better at some things and worse at others than any other, but it fits a nice spot on the design space. There are other related spots. For example, we ourselves have a query language called the categorical query language that has an interesting relationship to APG and is designed to do more, I guess, integration-y types of things, but there are certainly languages around it as well that hit other points in the design space. But anyway, hopefully that's a brief answer to your question, but a full answer will definitely have to be something to talk about offline. But other questions from other folks?
Brian, related to that, would you say basically that the APG is like a ring structure mathematically, or a group structure, and that if you take take something which is an APG and add it to something, it winds up being an APG? Is that sort of what's going on?
Yes. So that's exactly what's going on. It's not that APGs are rings, but APGs, for example, form a category in which you can have products of them or co-products of them. And in fact, there's different ways to even do that, but that's essentially the key insight, right? So what we did, for example, is prove that all the algebraic property graphs together, as well as the transformations between them, forms a special kind of category that supports things like adding them and multiplying them and lets you stay within that class. So yeah, that's a good insight.
Perfect, thank you.
Sure, other questions? No. All right, well, let's dig into the details, which hopefully will be of interest to this group since it's basic category theory with a little dash of, I suppose, type theory thrown in. So as Josh alluded to, the basic idea is to just define something called an algebraic property graph. So we're going to call it G. However, before we start, we want to fix in advance a set of primitive types and primitive values. So everything we talk about here is parameterized by, you know, do we have integers and strings, or strings and booleans, or what have you. But with that in place, now we have an algebraic property graph that assumes those base types, and that consists of 4 sets and 4 functions. So the algebraic property graph itself we call G, and the 4 sets are the set of labels. So these can be anything, but usually we think of them as, you know, person or name or something meaningful to humans, like that came out of a database. We have the types. Now this is a structured set. So whereas our set of labels can be anything, person, name, cheese, like a chair, right? The types actually are given as terms in a grammar, right? So we have structured types in algebraic property graphs, and this is how you build algebraic data types, essentially. So bearing in mind we have a set of primitives and we have a set of labels, right? That we're gonna use to define what our types are. what this is saying is that a type is either an empty type, which we're going to write as 0, a singleton type, which we're going to write as 1, a sum type, which we write as plus, a product type, which we write as the time symbol, or a primitive type, string, int, bool, or a label type, such as person or name. And that this is a little context-free grammar here, right? So there's infinitely many types you can write. You can have, 1 plus 1 and 1 times 0 plus 1 plus George, for example. But these, the set of all of those things is precisely the set of types that you can put in an algebraic property graph. And there is a little bit of flexibility here in that, we can extend this with, list types and set types and et cetera, but we at least want to have 0 and 1 and plus and times and primitives and labels to form like the core calculus. And of course, plus and times correspond directly to, either and tuples and Haskell. So this is the basis of all the algebraic power. I'll pause there. Questions on labels and types? Okay. Then what's the other half of a algebraic property graph, if you will? So I kind of think of labels and types as the metadata, and then the elements and values as the data, but as defined here, there's not really a huge distinction. So anyway, we have another set that we call the set of elements of G, and these two can be whatever you want. Usually they're going to be like identifiers, in some database, but in principle they could be, chairs or numbers or what have you, just some set of elements. And then there's also the set of values of the graph. So just like the types were defined as terms in a grammar, the values in an algebraic property graph will be defined as types in a grammar. So these are actually terms that are themselves typed according to the types that we have up here. So for example, there's a term, a value you can write down in an algebraic property graph called the empty tuple. It looks like these parentheses. It is a term of type 1. If you have a value of type T1, then you can create a value of type T1 plus T2 by doing an injection, right? Think Haskell here or Scala. So what we're building here with the values is essentially just algebraic values that correspond to the algebraic types that we have up here. So in addition to in left and in right the injection, there's tupling. There is a notion of a primitive, right? So if you had, integers, then we would expect, constants of 0, 1, 2, 3, for example. And then each element that you had in your set GE shows up as what we call an identifier here. So we're basically building out a little product sum type theory based off of the primitives and the elements in this set GE, and they're all naturally typed as you would expect. So that's the bulk of the data that's in an algebraic property graph. Now there are 4 functions that, actually let me pause here for questions. Questions on the elements or the values of the graph?
Is this on?
Yes, we can hear you.
Oh, good. Hi, Ryan.
Howdy. What's your
Paul?
Paul.
Yeah. You're laying out some. You're using terms that are ubiquitous in the data DBMS lingua franca, so to speak. And was your intention when you laid out this looks like math, to create new lingua, or were you trying to define what has been out there for some time?
So the point of this paper was to communicate a new data model to an academic audience. What you're seeing here on the screen is just a definition of a set valued functor, essentially, right? We're defining 4 sets and 4 functions, and we're using machinery such as context-free grammars to do so. So, a lot of these concepts are not new, things like product types and sum types, but all you're seeing here is just a definition of a structure that we're going to prove theorems about later.
I see elements. So elements, usually we refer to elements in a describing the elements represent unique.
Oh, so
Like
there's no meaning
labels.
to any of this, right? It's just let GE be a set, and we're just going to call whatever that set is the elements, right? They don't have to be anything. It can be a chair, it could be a number, it could be a color. Like it's just a set, and we're just going to call the members of it elements, so that we don't have to constantly say GE instead of the set of, right? So there's no meaning behind any of this.
No. What I'm talking about is they have a theory called retroactive inhibition. What you've learned in the past is affecting you learning something new in the future if the new thing in the future is a different definition of what you've learned in the past. And I guess I was trying to clarify, are you using the kinds of things, elements and labels and types pretty well label we used to call attributes for defining a database.
I wouldn't don't read too much into these terms, right? Instead, you could say a set G of L, the members of which we call X's, right? A set GT, the members of which we call boxes, right? It's, these have an intended use later, but at the level we're working now, this is just math, right? GL is a set.
Right. No, it looks like math, but I see some database constructs, and so I'm kind of honing in. Oh, this is where you put the attributes. Attributes would be like elements. Attributes and elements you would define it as part of a. I guess you're using class today, but if you were going to set up a schema, you would put those in there. So I was honing in on this. I know there's a this whole.
Well, let's take this offline, because I think it's orthogonal to the point of just presenting the mathematics here. But yeah, I'm happy to chat later.
Maybe I can chime in on elements and labels. So those are terms that are taken from the property graph domain. So if you go and look at, for example, any graph in Tinkerbell, we call the vertices and the edges of the graph elements, and elements can have properties. And every element, every edge has a label. And that's basically the name of the, in APG, that's a name that we give to the type of the edge. Vertices may or may not have labels in typical property graphs. In APG, they always have to have a label. So that's where those terms come from, just in terms of, etymology.
Okay, that was helpful.
Okay, other questions?
Similar to previous person who asked a question, I would like to ask you whether is it your invention, algebraic property graph, or it existed before in this huge field to my understanding?
So property graphs have existed for a while now. The first kind of well-known property graph database was Neo4j, and they kind of introduced some of this vocabulary, a database of nodes and relationships in the case of Neo4j, and then in Tinkerbell we called them, elements and vertices and edges, which are elements.
And algebraic?
And algebraic came from the unique requirements that we discovered in Uber with respect to making these things into a graph.
So it's your invention. It's new, novelty.
Right. Yeah, I haven't seen type algebras applied to property graphs before.
Got it. Thank you very much.
Otherwise, we'd probably be using that instead of creating a new data model.
Got it. Well, thank you.
Always fun to create new data models. Other questions? Okay. So there is some discussion in the group chat about the values here. So the idea is that, or the base, how the values relate to the built-in primitives, right? So the idea is that for each base type you have, like integer, say, and string, there's a set of associated base values. And then down here, right, your primitives, you can inject those in exactly the type that they're the value of, so that you know, you can have like 42 as an integer and 42 as a string, but not say 42 as a Boolean, depending on how you set up your primitive types and all of that. So, okay, cool. Sounds like the group chat, the question is answered. So, right. So in addition to these 4 sets, there are, of course, these 4 functions, or I guess not, of course, I haven't really defined, you know, the motivation for this, I suppose, but there are 4 functions between these sets that form a square when you draw the functions in a diagram. So they're pretty simple functions, right? So there's just a function that consists of data. It associates a label to each element. There's a function that associates to each element a value of it. So that's also data, right? So these are just some examples. Then the ones that are, so you can think of these as data, if you will. These others are more derived, if you will. So, or sorry, there's one more that's, yeah, go ahead. Oh, what, you have a question?
Yeah, I'm thinking back. Yeah, I can see working up the chain. These 4 sets you've got values is those are instances. I'm relating this to how I would do a database design in either a hierarchical or a network model. You know, many to many or one to many relationships. I'm thinking in terms of that, and I guess what you and Ryan are trying to do is reduce this to math, and the math will. Or visual, this, I guess, graph, there's some way you can visualize it, whereas the math piece, so you're saying, do we have all the relationships?
Maybe we should jump to an example, but yeah, I mean, the idea is to define an algebraic property graph as 4 sets of a certain kind and 4 functions, so that we can reason about them.
You can see if it's a mathematical way to prove whatever you're trying to model is complete. Right, that's what your ultimate goal is here, right?
I mean, it's just a data model, right? So in the same sense that the relational model has to define what relations are, we're just saying what property graphs are, right? So it's,
well, no, okay, I break the world down into structured and unstructured modeling. Structured would be a network or hierarchical models. Like IMS would be a hierarchical, and Codicil would be like IDMS. I'm going back to the 60s here. And then,
okay, we should talk about that offline though, because I do not believe most people here are familiar with those technologies, but I am hoping at least that the math here is clear, right? These are 4 sets. Everything here is formally defined, right? We have this proved in a proof assistant, right? So you can check it down to the level of bits, but it's, you know, 4 sets and 4 functions that we can, you know, interpret as property graphs. Are there other questions before moving on to an example thereof? No. Okay, cool. Right. So yeah, just to finish off this little section, right? So there's 4 functions. For each element, we have a label. For each element, we have a value. For each label, we have a type. So we're saying, for example, the type associated with name is person times string, so that you can think of this as all additional data that comes with an algebraic property graph. Then there's a function that's just a derived function, right? That says, here's the type associated to each value, that you can basically just read it off though, right? Because each of these values is a term in a grammar that has an associated type here on the right. You can literally just take it from that. So this is just a function that exists not as data. And then there's one key requirement, which is that those 4 sets, these G's, G of E, G of E, G of L, G of T, and the 4 functions, when you arrange them together into a diagram, right, like this, where the functions are arranged, you know, domain to range, that this equation holds, right, which says that if you start, for every element in your graph, if you find the label for it and then look up the type, that type is the same as if you look up the value associated with the element and then take the type off of it, right? So basically it says that the elements have values that have the types according to the schema. And so that is pretty much it. Actually, that's not pretty much it. That is literally everything, the definition of an algebraic property graph. So we can think of this as 4 sets of a certain kind and 4 functions. We can think of it as a set valued functor from the category with 4 generating arrows in the category of sets. There's a way to think about an algebraic property graph as a canonical type theory. That's how we implement it in CQL, for example, and a variety of different ways to think about it. But at the end of the day, it's 4 sets, 4 functions, where the types and grammars are formed according, or the types and values are formed according to these grammars here. So I'll pause there before getting into examples. Is the definition clear?
If you go back up, move up, page up, I can see where values is uneasily. Label is what the difference between type is obvious and values are obvious. The distinction between label and element.
Just 2 different sets. They're both just whatever you want them to be. So
label is using they don't see okay, so label you're using where you use label now. In the past I've used elements. Those are elements.
Sure. I mean, it can be whatever you want, right? It's just a set. Yeah.
Okay. All right. No
Does the label have to be unique?
I mean, you do need a set of them, and we're going to give a function from entities to labels, so they have to be unique in that regard, right? This has to be a function.
That's a good question.
You can't call everything an apple. Okay, well, that's all right. Then it's...
No, I mean, you could, right? If you only had one label, for example, all your elements have to be assigned to that label. So, every element has to get exactly one label. So if you have elements, for example, you have labels.
Element, a child of the label?
No, it's just another set, right? Just another set GE, the members of which we call elements. It's just a name.
I don't know what elements does here then, because I'm used to you.
Let's go to an example.
All right.
So an example is, man, I guess this is written as prose.
Well, that kind of goes along with my my drove for example before. Let's say nose instead of drove for. Scroll up.
Oh, could we use this one down here?
Oh yeah, that's fine.
Okay.
You've got another one in mind.
How about this? Right. Yeah. So here, and this may or may not be complete, but it happens to be what we just scrolled into, right? It reveals some of this. Actually, reveals two different graphs, G1 and G2. Maybe this is not a good example. Scratch that. Go back up. Find an example of just one property graph. I guess we'll work through this one. So, okay, what is this? Section 4, actually. Okay, yeah, we can work through here. So Josh has developed an entire taxonomy of property graphs, actually. So, before we just gave their definition, right? This is an algebraic property graph. And then the pieces of the paper that we skipped just now give properties of algebraic property graphs. Like here's how you multiply them, here's how you add them, that type of stuff. But then there's actually a taxonomy that you can put in place onto the elements themselves, or is it the labels themselves, or is it actually both? I forget. Josh will have to speak to that. But depending on the properties that particular elements and labels have, you can describe them and give them particularly descriptive names. And so that taxonomy is a rich source of examples. And then the taxonomy itself has some utility for other purposes. So here's an example then that illustrates the idea of this thing called a vertex label. So this is a graph that has a label where the associated type in the schema is the unit type. So, all right, here we go. So we have each graph has to have a set of labels, that's GL, a set of elements, that's GE, a set, and then the types and the values are fixed, right? So we just have to give the labels and the elements. So 2 labels, user and trip, two elements, U1 and U2. And the schema, so this is a function we have to give sigma, it associates each label to the type 1, right? The unit type. So that's the schema right there. There's really nothing being recorded in it, right? This is a kind of an uninteresting assignment, but anyway, then the label of the element U1 is a user, and the label for the element T1 is trip, right? So this is basically saying we have a user U1, we have a trip T1, and no other information recorded about that whatsoever. So a bit degenerate, but it's good to have base cases. Let's pause here on this example and at least make sure that sort of everyone understands how this is an instance of the formalism presented in the paper.
And let me add to that by saying a vertex is one of these pre-existing concepts that you'll find in property graph contexts. So a vertex is just something that has no internal structure. So that's why the label of any vertex maps to the unit type. Unlike an edge, which has components in it or fields. So an edge has a head and a tail, or an in vertex and an out vertex. It points from something to something. A vertex has no such internal structure. So that's why you see a trivial type for vertices, and then you see a product type for edges.
Right. So in fact, we can move on to that more complicated example. So here there's 4 labels: user, trip, driver, and rider. 5 elements. Looks like we're going to get 2 users, 1 driver, 1 rider, and 1 trip. Just sort of as a guess, but we can see here in the label assignment, that's exactly what it is, right? U1 and U2 get sent to user, T1 to trip. So thoughtful choice of variable name of element names there. Here also the user and trip are assigned by the schema, the terminal type as before, but these new labels, driver and rider, are assigned product types. In this case, trip times user. It looks like they're both the same. And then let's see what else is going on here. So of course, the values associated with all the unit type things have to just be the empty tuple according to the type system. Oh, and then we have to give data for the non-unit type things, right? So we have to give driver and rider data, and these are trips times users. So we have to give pairs of things, right? But fortunately, we already have a trip called T1 and a user called U1, so we can include these here. And so, technically, there's, we should say, this is the insertion of element T1 into the values, blah blah blah. But this is the data as you would expect. And so let's see if there's a picture of that one. No, not so much. But anyway, that's a more complicated example that hopefully sort of reveals that the formalism, while having a lot of stuff in it, is actually just sort of type theory, like you might find in Haskell. Questions here on either of these 2 examples?
So yeah, the gist of it is that we take these, again, these pre-existing concepts, vertices, edges, properties, for which there's never, well, there have been a few more formal data models that have been defined for the sake of, mainly for defining mappings. But they're a bit, there's nothing that's been really elegant, in my opinion, that's been, just a nice simple data model that captures the simplicity of the concepts themselves. Some types and product types, in my opinion, do that very nicely. You can think of, any of these things, vertex, okay, it's just an empty tuple type. An edge, it's just ordered pairs. Properties, that's just ordered pairs where the first element in the pair is another element. You have vertex properties. Well, that's just the type of a vertex property is something whose schema has a vertex type as its first element. I shouldn't say element, the first component. An edge type, which is another concept, of attaching an attribute to an edge, essentially. The type of that is just something that has an edge type as its first component. So it gives you a nice framework for expressing these things formally.
What does Uber use the taxonomy for? Or is it just to refer to things in this way, or is there some like deeper motivation for sort of how it originated?
Well, again, there's my bias as you know, with my graph background. I like to think of these things in terms of vertices and edges and properties and so on. But we actually use, if you scroll down, we use hyperelements in practice and rarely use vertices and edges. There, like I say, there is an Uber knowledge graph, and that does use a graph data model that its schema language is something that was kind of a precursor to this language and is more RDFS-like. But for most data at Uber, we don't speak of edges and properties and vertices. We do occasionally speak of entities, but they're essentially just, you know, again, product types where the product might be, you know, have an arity of more than 2, or it might have more than 2 elements. So instead of an edge, which is binary, like that drove for edge, you have a you know, a user who drove for a trip. In general, we just have these product types that may have 2 elements. They may have more than 2 elements. So this this example here is of a trip, where a trip, you know, contains 2 users and 2 place events. And like I said before, it's kind of a simplification. There's other things that are in our trips in practice. But you can think of it as a vertex because it's identified by a unique ID. You can think of it as an edge in different ways. So you can think of it as an edge connecting a user with another user. You can think of it as an edge connecting a user with a trip in a couple different ways. You can think of it as an edge connecting a person with the place they were dropped off or the place they were picked up. Or you can think of it as connecting the driver with the place that they picked up a passenger or the place that they dropped off a passenger. And that's just kind of the difference between a binary relationship and a hyperelement, which can be more than binary.
Gotcha. Okay, cool. Are there other questions? If not, I think what to do is I'll briefly overview the other operations you can do on APGs that we haven't seen yet, and like things like add them, and then I'll show APG in the CQL tool, and then we can call it a night. But I'll pause first. Questions here?
I just had one, which is, what if I'm driving a car and the user wants to go from Manhattan to Staten Island over the Staten Island ferry? How do you handle, is that just get added in terms of the cost per the unit of moving? Or are there actually 2 things going on, and how does that work with this?
Oh boy, I don't know. Is that a competitive secret about how Uber operates?
No, it was just
I love the question.
It's just a question about how do you handle the mathematically. I mean, there's probably a simple answer. I just was curious.
How would you model that? I'm not sure. What, can you repeat the scenario?
Okay, so I'm sitting at Battery Park, and the user gets in my Uber vehicle, and he says, I want to go to Staten Island. So you have the vehicle gets on the Staten Island ferry, and then there's this charge based on, you know, okay, from this point to this point happens to be on a ferry, and you're going to get charged differently from when you get off and you're on Staten Island in terms of the rate or something like that. That was
okay.
So that's an interesting scenario, but has little to do with graphs.
Well,
yeah, I better not get into.
There's a point A and point B, and they're connected. But
or maybe the thing to say, to speak to here, Josh, is what all this graph data actually is inside of Uber, right? Is it the trips? Is it something else? Like, what is all this graph data going on in there?
So there first of all, we have data. Did not start as graph data. APG is a way of thinking of it as graph data, but most of it, the vast majority, was not designed as graph data. So for example, there are tables that deal with trips that contain all that information about, the pickup point, the drop-off point, the rider, the driver, different attributes of the trip. And you can think of those as a graph, and it can help to think of them as a graph when you're, say, aligning data sets, and you have an ID type in one table that corresponds to an ID type in another table. For example, in a trip table, you've got an identifier for the rider and an identifier for the driver. If you assign types to those identifiers, then you don't have to guess that, say, in this other table that deals with users, you want to find, say, something simple like the name of the user. Well, you already have that type that connects the field in the one table with a field in the other table. So you can think of that as just, primary keys and foreign keys, but it's done on a type level rather than a table level, and that's something that.
Say that again.
Which part?
I was following you. You said primary keys, secondary keys, they're the same in multiple tables. That develops a relationship. So you were saying what? By the algebra.
So one way you can bring those two tables together is to declare that, say, the user ID key in your trip table corresponds to the primary key. So it's a foreign key reference to the primary key of your user table. And based on that, you can get the name of the rider or the name of the driver.
You have to do that in relational databases.
Yes, you do.
So
but if you use types and you think of the data set as a graph, and you've assigned a type to the rider field, and you've assigned a type to the table that represents users, then in principle you can automate some of that rather than.
But you have two fields, and you get the same field in two different tables, and they are the same entity, or what? They define the relationship, whatever key you're talking about. So how are you relating that in your language here?
So that's where you would use a type for, say, the primary key of the user a user table.
So they have the same name and the same type.
They don't have to have the same name. They would have to have the same type. So if you found the same type in two different tables, and that type has the uniqueness attribute that I mentioned in my slideshow, then you'll know when you find a user ID in a given table, like a trip table, that you can join that on the primary key of another table, which also happens to be user ID.
Right, but what makes, so if the names that don't have to be the same, if you don't use the same name in both tables, there are other attributes that tell you that they are the same and at the same time unique.
So that's the point of we're pushing for reuse of standardized types, not so much at the table level yet. That's some of the connected data stuff that I'd like to get into in the next.
You mean index here, don't you? These are indexings.
Yeah, I mean, you can use.
Not just a field, these are same index. Or
you can use a unique field as an index. So you can use it to tell you that you could index.
Secondary keys, primary keys, right.
So that can be used as a hint to create an index in principle.
Okay, maybe we should set that one aside. There's 15 minutes left.
Okay.
Yeah, I would like to actually show the CQL tool and such. Josh, were you about to say something?
Did you want to say anything about transformations?
Ah, right. Yeah, and that was actually a natural segue. So in APG, you can, with the taxonomy, say things like this is a node, this is a vertex, what have you, but actually querying an algebraic property graph or merging two of them or what have you, we haven't talked about yet. And so what we did for the paper and what's implemented in the CQL tool is these operations on APGs themselves, such as joining them together or what have you. So I'll just briefly outline what these results are and then show the tool. And the basic idea, this being category theory, is that we're going to look for universal constructions in the category of APGs such that those constructions correspond to things like conjunctive queries or what have you. So as a technical note, we're going to form a variety of different categories of APG that will have different notions of morphism, because depending on what you're doing, like if you're querying or integrating, then sort of the things in a graph you may want to hold fixed versus let vary can depend on what you're doing. But they all, the notion of morphism of APG that we'll be using, they all restrict like the notion that we defined earlier as being a natural transformation between set valued functors. So anyway, there's probably not enough time to get into all the details, but what are some of the cool stuff you can do query-wise? So the category of algebraic property graphs, you got initial and terminal objects, so like a sort of something that operates like a 0 and something that operates like a 1, plus and times products and co-products. You can union APGs together, you can multiply them, you can join them. So there's a way to do conjunctive queries with them, right, where you so that's essentially, or that was, theorem 1, that this is a useful formalism that because the APGs form a bicartesian category with these things called equalizers, that means that conjunctive queries, select from where types of queries can be performed on APGs. So that's some good news, and that's implemented in the tool. Other stuff you can do. So in addition to query APGs, you can integrate APGs. So that's the next theorem, right? So just as before we had equalizers that corresponded to queries, we show that you can do something called co-equalize APGs. And what that does is form like a union merged type of APG where you union your data, but then maybe you want to equate trip 1 and trip 5 because you found out they were the same. And so that's a data integration type of operation. And so we prove that in certain cases, co-equalizers of APGs exist, and then that's what we would use for data integration type of operations. And there's a big example in this paper. And then finally, the last class of things is, so we talked about query, integration, and then we have migration. So you can think of migration as a special case of integration, but it's might even be more fundamental, which is just that here what we're going to do is change the schema that an algebraic property graph lives on. So we have to define, what a morphism of schema is, and then we end up proving that you can in fact migrate algebraic property graphs from one schema to another. So this is actually the contribution of CQL here, which is that notion of data migration for algebraic property graphs is a special case of what's built into the CQL tool. And with that in mind, I'll just break that thing out and show folks questions.
To pick up on your last point about the data migration, I've been trying to to understand the paper in CQL in the context of that kind of work environment of data integration. I'm not there yet, though. I'm trying. And in the context of building the kinds of pipes that you do in that work for putting together, the data processing pathways to support analyses and applications, artificial intelligence downstream. I'm trying to see where the clear advantages. I mean, I get that it's a layer of abstraction on top of it. It has, and that's valuable in its own right. But where do you think like any kind of work saving is? Any kind of efficiency in kind of the, might say the dirty work of building those kinds of pipelines, the plumbing work?
Right. So there's probably a two-part answer to that, and Josh can speak to the value proposition at Uber, and then I can speak to what we see as the value proposition sort of outside of Uber. Do you want to go first, Josh?
Sure. So there's a few different ways in which a consistent and unifying data model helps. The one that's been explored most so far at Uber is just simple schema integration and migration of schemas between languages, like I talked about in my slideshow. Just the fact that we're able to define standardized data types in a single language and then map them into equivalent types into each of the lower level languages that we use for data storage and data interchange does save time. And that's the basis on which we initially justified the project, is that we have a tremendous amount of duplication of types, and simply providing standard controlled vocabularies in a central place saves time, because developers can then just reuse those types. And we've had pretty good success so far with reuse. So that's one way in which time is saved. Potentially, looking forward past schema-based operations and moving into more data-based applications, having standardized types as annotations on your data sets, sort of like what I was talking about with Paul, allows you to do some interesting things, potentially, including data discovery, included automated data categorization, which is a big one right now, with things like GDPR to deal with, so privacy regulations. We need more understanding of our data than we previously needed when the company was younger. That's potentially a $5 billion problem of protecting users' data in a way that complies with these policies. So having a common language, we think, is going to be a very valuable thing. I don't even see another solution to that problem than being able to apply annotations in a standardized and consistent way to all of our data.
And so my half of the answer would be that, we at Connexus are thinking outside of Uber about the operations in APG that are in the paper but haven't really been put to work yet, right? So these things like the co-equalize operation I was describing, like, this is an operation that can be used to do data integration on data that already exists, right, with very intuitive semantics. So just scrolling through some of these examples, right, where you see very natural constructions on things like license plate numbers, where what the semantics of the data integrations are doing is like forming equivalence classes, for example. So, but we see our next generation operations in regards to data that don't exist in any tools yet, but that do interesting and useful work to the data to help you get insight out of it. And so that's where our interest is. And the tool that we're deploying this month, it's doesn't work on algebraic property graphs. It works just on SQL, but it really it lets you translate queries from one schema to another with just the push of a button. So that alone is pretty large time saver, but it all hinges on creating nice schema mappings, which themselves depend on having a nice mathematical model that supports all the kind of reuse that you want. So a bit long-winded, but does that answer the question?
That says a lot. Thank you. Yeah.
Cool. So with that in mind, there's 5 minutes left. I guess we should probably just pause for any other questions here at the end. But basically, people can download, this is the CQL tool I'm showing. There's a built-in example called APG. Everything that's done in the paper is implemented algorithmically in here. So there's examples of conjunctive queries. There's examples of adding graphs, multiplying graphs, exponentiating them, equalizing them, and then all the proofs are done in a proof assistant as well in GitHub. So it's solid at a technical level, but do please, download this. Uber's repo hopefully will get open source sometime soon, and there's a relationship with Tinkerpop 4.0 and a lot of ways to get involved. So With that, we'll pause for last minute questions. Anyone want to speak up?
Yeah, by the way, if there's anyone who thinks that you would really like to use this tool, testimonials would be appreciated. So one of the things I'm trying to do is demonstrate the community interest and the potential impact outside of Uber. So if you have anything to say, feel free to chat here or in the on the Meetup group, or send either one of us an email.
Joshua, I joined late. Did you say what data DBMSs they use at Uber?
I said a few, yeah. I could go back to that slide, but there's we're pretty heavy on Hive, and I want to hesitate to say too much because this is not my area, and I don't want to say anything that wasn't in the slides. But we do use MySQL. We have something called Schemaless. We have another thing I'm not sure if I can name. I haven't put it in my slides, so I'm not sure. But we have a variety of backends for offline storage. Cassandra is another.
Schemaless meaning.
Go ahead.
Schemaless meaning it's object. It's a NoSQL slash NoSQL type of object model.
Yeah, it's a little bit of a misnomer because it does include schemas. But I'll send a link if I can find one.
I was just thinking of it generally. I don't really need detail, just looking at what generically they were using.
Yeah, I don't know if I can, I'm wary of veering off topic because there are certain things that, I've gotten the, approval to talk about, and everything else I should probably just save for offline chat. If there's been an article published about Schemaless in the Uber Ends blog, then certainly I'll point you to that and we can talk about it.
Okay, I guess we can call it a day. I would like to point out one final thing, which is just for all the Haskellers who are here, right? Which is that the notion of mapping of APG schemas looks a lot like code you would write in Haskell, right? So, everything's always one and the same, but there's little lambdas and bound variables and all kinds of stuff. And so with that in mind, yeah, I hope functional programmers especially become interested in it because it's a cool little framework. So any other questions before we part? Sounds like the answer is no. Cool. All right, everyone. I will post the video and the slides, which are already available on the Meetup for anyone who wants them once Zoom finishes recording them. And then we'll regroup next month with hopefully something just as interesting. Thanks, everyone, for coming.
Sounds good. Thanks, everyone.
Thank you.
Thank you.
Ryan, are you still there?
Yes.
How are you?
Doing all right. How are you?
Very good. Oh, yeah, I didn't want to get asked specific questions here. Just get an idea of what the big companies are using for their databases, and then from that, I was inferring that the things you're working on are to solve a problem, and it looks like to me that there's no structure, relational, and now no SQL. I don't think they mean no SQL. I think they mean no schema, but they're using the document object model to load the databases. But when you do that, which all these internet companies are using now, there's no schema that everyone can reference. And I guess you're trying to provide mathematical tools that would allow all the people that need to outside the developers, one of the data science people, to understand where the data is. You're giving them a framework in a mathematical sense or in this graphical sense, trying to simplify understanding of what this conceptual data model is, I guess. And that's a very difficult job. So it's you've got a very difficult load to be able to do. So I appreciate any work that you do on that in that area is appreciated.
Oh, thanks for your kind words. It's a dirty job, but somebody's got to do it.
No, it's a very difficult job, and I don't see there's any tools out there. But that's where I guess where we're at.
Cool.
State of the art is at that place.
Yeah, I mean, this was a research paper, right? What we presented here. So it is, there are no tools. Hopefully this is the first. So yeah.
It's funny, it comes out of the math. You both of you guys are very math majors, right?
Something like that. Yeah.
I know you are, and Joshua, you come from the math background?
I'm not. I'm from a computer science background with
Okay.
some physics thrown in way back. But
Well, there's a lot of high calculus in there, so I appreciate seeing
He looks like a math guy. You look like with your set math guys. I had a guy from MIT also was a math. He was the. I always lean whenever we got into the math. I would lean on them or defer to them for their understanding. So
Following the mathematicians is usually wise. On that note, I do have to run. I got a hard stop at 8, but this was a pleasure, and I'm looking forward to seeing all of you at the next one.
Thank you very much. It was wonderful.
thank you.
All right.
Excellent job. Thanks a lot.
And thank you, Josh, once again for the nth version of the talk.
yeah, thanks for making it happen.
All right, see you guys.
Thanks,
Good night, everybody.
Joshua. Thank you very
you.
much.
Bye. Bye.